In the last video, you learned that simple loops run in linear time or O of n. But here we have nested loops. This is the algorithm that we use for printing all combinations of items in an array. So what is the runtime complexity here? Well, let's find out. In our outer loop, we're iterating over our input array. So here we have O of n. Now, in each iteration, once again, we're iterating over all the items in this array. Another example of O of n. So the runtime complexity of this method is O of n times n, or n squared. We say this algorithm runs in quadratic time. As you can see in this diagram, algorithms that run in O of n squared get slower than algorithms that run in O of n. Of course, this depends on the size of the input. If you're dealing with an array of, let's say, 50 items, we're not going to see any differences. But as our input grows larger and larger, algorithms that run in O of n squared get slower and slower. Now, what if you had another loop before or after this loop? For example, let's add a for loop, and once again, iterate over all the items in this array and print them on the console. What is the runtime complexity of this method? Well, here we have O of n. So the runtime complexity of this method is going to be O of n plus n squared. Now, once again, we can simplify this. The square of this number is always greater than the number itself, right? So in this expression, n squared always grows faster than n. Again, we use the big O notation to understand how much the cost of an algorithm increases. All we need is an approximation, not an exact value. So here we can drop n and conclude that this method runs in O of n squared. Let's look at another example. What if instead of this loop, we had another nested loop here? So for int of third in numbers, there you go. The runtime complexity is now O of n cubed. As you can imagine, this algorithm gets far slower than an algorithm with O of n squared.